Hello everybody, this is Team 19, Kemi and the Beast, and we're here to propose our design of a methanol plant. This project is brought to you by Brian Shoemaker, Edward Brand, Abdullah Naki, William Sins, and Quo Tran. So the purpose of this project, like I said earlier, was to create a chemical plant that refines our natural gas into methanol and sell it for profit. So we're going to start with a feed of 513 million pounds per year, and then we're going to get as a product 813 million pounds per year of methanol, which we're going to sell it, and then at the end we're going to see whether this makes a profit or a loss, as we'll discuss later. So this presentation will be divided into four main parts. The first section will be project background, in which Brian's going to talk to you about methanol and its current uses and applications around the world. He's also going to talk to you about the supply and demand of natural gas and methanol. Next up, we're going to have Abdullah talk about his process overview of the plant, where he separates it into three main phases. He's going to talk about pre-treatment, then he's going to talk about synthesis, and then he'll finish it off with purification to meet our product spec. Then Edward will talk about two other alternative designs in which we remove and add other units to the plant and decide what differences happen. Then we're going to hand it over to Quo, where he's going to talk to you about safety, and he's going to talk to you about a brief HAZOP that was conducted to identify any potential risks that can occur in the plant and how to prevent them. And Ed will also talk about the process control strategies implemented in the plant. Next, we'll finish off with Quo with an economic evaluation of the base case and the alternative design.
The feed stream that we are purchasing that will go into our plant is a natural gas stream. Natural gas, as you can see from the graph here, in 2007 began around 1 billion cubic feet per day, and then has increased in production to, in 2014, it's almost about 11 billion cubic feet per day. As you can see on the graph on the left, with the historical index of natural gas, the price has also been decreasing over the years. So as you go from 2000 all the way up until the current year of 2017, the prices are decreasing, making it a viable stream for us to buy for our methanol plant. The demand for methanol has been increasing because you can make methanol into many different compounds. It can be used as a starting material or an intermediate for formaldehyde, MTBE and TAME, acetic acid, and many others, as you can see on this pie chart. These compounds can then be formed into other household items such as resins, plastics, and other compounds that are seen in our daily lives. Over the last 3 decades, there's been an increasing demand for methanol. As you can see from the chart, in 1990 all the way up until the year 2007, there is a steady increase in the demand for methanol. This is because methanol can be used as an intermediate and a starting material for other compounds, as seen in the pie chart on the previous slide. Due to the increase in methanol demand and the decreasing price of natural gas, there is an opportunity to possibly turn a profit. Our target methanol production is 743 million pounds per year. As you can see from our current value of 813 million pounds per year of methanol production, we are producing methanol at a better rate than our spec. The target purity is 99.85%, and we are accomplishing that. You can see these 4 reactions that are occurring in the methanol reactor. 2 of these form byproducts, one being ethanol and the other being methylformate. These will have to be removed at some point in time after the methanol reactor.
So next up, we're going to be talking about our process overview, which is divided into 3 sections. First phase will focus on the pre-treatment of natural gas, and the second phase will focus on the conversion of natural gas to syngas, and then converting syngas to methanol. Afterwards, the third phase will focus on the purification of methanol. And so to start things up, we have our natural gas feed stream going into the absorber. The first absorber works on kicking out the acid gas. The acid gas removal is done by introducing an MDA stream that goes through the absorber. So we'll end up with two streams exiting, one which is the sweetened gas, which is sent to the glycol dehydration unit, and the other one is the rich MDA. The rich MDA stream is then sent to a regeneration tower, and that regeneration tower works on separating the acid gas from the MDA. The MDA is then sent to a mercury removal unit, since mercury was also removed throughout the absorption unit. After mercury is removed from the mercury removal unit, the MDA is then sent to a surge tank where there is a MDA makeup as well as water is introduced to make up for any losses. And then the exit stream of the surge tank contains the MDA solution that will go through the absorber again. So continuing on from phase one, our sweet gas is then sent to another absorption unit, which works on dehydrating the natural gas stream. To dehydrate that sweet gas, we introduce a lean triethylene glycol solution. This triethylene glycol solution separates the water and then gets sent to a regeneration tower in a similar fashion as the MDA absorption unit. The regeneration unit tower separates wet gas and triethylene glycol. Triethylene glycol is then sent to a surge tank where there is a triethylene makeup stream that makes up for any losses that occur throughout the process. The tops from the absorption unit is the dry gas, which is then sent to phase two of our process. So next up we have phase two with our dry and sweetened gas going into a steam reformer. So alongside the dry gas going to the steam reformer, we have also a steam going into the steam reformer. The product of the steam reformer is the syngas. Syngas is then cooled down and compressed and sent to a methanol conversion unit. But since the methanol conversion unit does not have a high conversion of syngas, we end up having products and excess syngas exiting the methanol conversion unit. The excess syngas and the products are then sent to the flash separation unit, which works on separating the excess syngas and then kicking out methanol and water at the bottoms. The excess syngas is then sent to recycle back to the methanol conversion unit to increase our yield. Methanol and water are then sent to phase 3 of our process, which focuses on the purification. So next up we have phase 3 of our process, which has methanol and water going to the first distillation tower. The first distillation tower works on separating a large portion of water from methanol at the bottoms, and then at the tops methanol and a little bit of water comes out. There are also non-condensables, which are mainly syngas in the process, which are then flared off of our process. Methanol and water are then sent to a second distillation tower that works at the similar fashion of the previous one, and then we'll end up with water at the bottoms, methanol at the tops, and also a little bit of non-condensables. The methanol purity determined at the end of the process was more than 99.85%, which meets the spec.
For our first alternative design, we completely removed the glycol dehydration unit. Since phase 2 operates at much higher temperature, hydrate formation is unlikely, and therefore hydrate line blockage will not occur. Furthermore, the waste stream from the distillation towers in phase 3 can be recycled back to the reformer due to majority of it being water. In doing so, this will save the cost for the wastewater treatment and the additional steam that will be required to operate the reformer. For a second alternative design, acid gas removal unit was replaced by a desulfurization unit. Desulfurization unit removes hydrogen sulfide and leaves carbon dioxide in the stream. Carbon dioxide is desirable because of the secondary reaction that is capable of producing our desired product, methanol. Desulfurization unit only uses activated carbon and does not include complicated acid gas removal system as previously described. In addition, exiting stream from the desulfurization unit does not contain a lot of water, and therefore glycol dehydration unit is unnecessary, thus further saving up the costs. And finally, wastewater from the distillation towers in phase 3 can also be recycled back for the reformer for the reasons as previously mentioned.
Throughout the phases of our process, we are exposed to many types of material, including hydrogen gas, methane, CO2, and carbon monoxide. These are all flammable gases, therefore the material construction throughout all phases of our equipment design must be considered. The materials of construction were selected to be either carbon steel and stainless steel to avoid explosions, accidents, or corrosive behavior from our chemicals. A brief HAZOP was conducted on various pieces of equipment. In particular, this one was the Fischer-Tropsch reactor. The Fischer-Tropsch reactor operates at very high pressures and temperatures ranging about 420 degrees Fahrenheit. Any deviations from these operating conditions will yield lower conversion of syngas to methanol. For example, the process parameter here would be syngas flow. If the syngas flow was too low, this could be attributed to a compressor malfunction upstream of the Fischer-Tropsch reactor. As the reactor pressure decreases, this yields a decrease in conversion, lowering our product production. Another process parameter would be syngas temperature. As noted for this reactor is very sensitive to operating temperatures. If it operates any higher than 400 or 500 degrees Fahrenheit, the conversion will be low. A deviation for this would be that the syngas temperature would be too high. This could be a result of a heat exchanger upstream of the Fischer-Tropsch reactor, a flow control valve malfunctions on a cooling water line on the heat exchanger and causes bad heat exchange upstream of the Fischer-Tropsch reactor. As the reactor temperature increases, the overall conversion decreases. So in order to avoid any process deviations, proper process control strategies were needed and employed on our equipment to improve operability and improve safety. This will be talked about by Ed.
As mentioned before, to ensure safe and stable process, several control strategies were employed in this process. Several control variables such as temperature, pressure, level, and flow were utilized in this design. Here you can see an example of controls. You can see a sensor attached to the distillation tower to monitor temperature. The reboiler, the signal is then transmitted to the reboiler where a valve regulates the temperature. Whether the temperature is needed to be too hot or too low, this control valve will be appropriately adjusted.
The total IBL equipment cost and OBL bids resulted in about $320 million of total cost for the entire plant. As you can see by this pie chart, the operating cost is made up of total raw materials, utilities, as well as labor, tax, and other fixed costs. The majority of the operating cost lies and exists with the total raw materials as well as the utility streams. In order to cut down our operating costs, an area where we were thinking, as previously mentioned before, is cutting down and recycling our wastewater from our distillation. This will cut down the 14% of operating costs resulting from wastewater treatment and could potentially impact the economic evaluation of our plant. In order to conduct a fair economic evaluation for our base case design, we were given that the price of methanol was currently at 12.5 cents per pound and that the natural gas feed is priced at 4 cents per pound. However, due to fluctuations in natural gas prices in the recent years due to the Great Recession as well as the oil prices of 2014, we decided to take an average over the period of 2008 to 2017. You can see these truncated plots for natural gas on the left and methanol on the right. By taking this average, the average price of natural gas feed is about 7 cents per pound, as well as the methanol price, product price being about 18 cents per pound. When using these two prices, the economic evaluation for the base case design yielded an underwhelming after-tax rate of return of about 3.12%. This does not reach our hurdle of our company, which is about 15%. Additionally, the net present value was about negative $85 million, and cash flow was $88 million. In order for us to reach the 15% rate of return, the required setback for the price of methanol needed to be about 24 cents per pound. Due to changing economic climates, the price of methanol may fluctuate over time. As mentioned before by Brian, there is an increase in demand for methanol, so we ran cases where we had methanol ranging up to 24 cents a pound. As you can see by this graph, the raw material margin, which is the difference between the product price and the feed price, must be at least 17.5 cents per pound in order to reach a product after-tax return of 15%, as you can see by this graph. If the product price was 24 cents per pound of methanol, the after-tax return jumps up to 18.4%. The net present value increases to $206 million, and the cash flow is about $861 million per year. It is important to note that the price of methanol was 24 cents per pound at its peak in year 2008. This has only happened one time over the past decade. In addition to running economic sensitivity tests on the raw material margin, we also considered 4 different sensitivity analyses. The first one includes decreasing the capital cost of our plant by 20%. The second one is accelerating our operating capacity after the first 3 years of construction. Furthermore, we also wanted to see what the effect would be if we increased our plant capacity, assuming that our total plant costs remain the same. Finally, we were also interested in seeing what if we moved the plant from the Philadelphia, Pennsylvania location to Houston, Texas. As you can see by this graph, it is apparent that the base case design is well under 15% after-tax return. This is very underwhelming, but if you consider the alternative design 2, it is apparent that it reaches closer to 15%, especially if you increase the plant capacity. Further, while these rate of returns for the alternative design 2 is very close to 15%, which is the company's hurdle rate, we would like to see something a little bit higher on the magnitude of 20%, 30% to comfortably move forward with this project across all designs.
So in the end, we conclude that since the base case did not reach the required after-tax rate of return, which is 15%, and it had a negative net present value, it would not be feasible to build this plant because it will not be making any money throughout the lifetime of its 3 years of construction and 15 years of operation. If we use our conservative estimates of natural gas and methanol after the Great Recession, we will not be making money as well. If we price methanol at 24 cents per pound, then we'll be making an after-tax rate of return of 18%, which is a little bit profitable. The only way we'd be making money is if we consider the alternative design, the second one, and that is because we eliminate a lot of elements from the pre-treatments, as well as eliminate the cost associated with the outer barrel limits from the water waste that is being kicked out of the distillation towers. We'll be making a large amount of money, having a net present value of approximately 250 million if we use the second alternative design study, as well as optimistic values, with the natural gas price being at 4 cents per pound, as well as methanol being at 24 cents per pound.
That concludes the presentation of our proposed methanol plant. We would like to thank everyone who was involved with this project, including Professor Don McFadden, our TA Amanda Yang, Professor Bob Nedwick, as well as our 2 mentors, Alexander Okert and Jessica Geis, for their guidance throughout the entire semester. Thank you for listening.